Okay, so welcome everybody. Our guest speaker is Professor Sebastian Szybka, and he will tell us about toy models of standing gravitational waves. Please, Sebastian, begin your talk.
So thank you for invitation. I'm Sebastian Szybka from Kraków, speaking to you live now. I work in the astronomical observatory in Kraków, and I will try to convince you today that there is an interesting topic, and the topic is open, so there's still a lot of place for progress here. And the topic is standing gravitational wave. So the main idea behind this talk is that in physics, wave phenomena is something like very, very important. It appears in all the branches of physics. And nowadays we live in the era of gravitational wave astronomy. So we have theoretical prediction of existence of gravitational waves. That is one thing. And another thing is that the gravitational wave exists because we can observe them and detect in our detectors. And there is, like, in my opinion, like important omission in our knowledge on gravitational waves, because in all the other branches of physics, where you have the wave phenomena present, there is like a special class of solutions, of wavy solutions, called stationary or standing waves. So I will just, the main motivation, it's given for this study in the paper that is already almost 20 years old by Stephani from 2003. And he asked there a question: what is a standing gravitational wave? So we try to understand this phenomenon. So just short reminder, what is a standing wave? So the most basic example you may see now, I hope. So it's like a one-dimensional wave, and its mathematical description is very simple. So you can think about the violin and the string of the violin when somebody plays the music. This string is attached at two places, and it oscillates with this pattern that there are points called nodes, which are not moving really, and the places where the oscillations are the largest, have the biggest amplitude, are called antinodes, this solid vertical line that you may see here. And this is a snapshot at two instants of time, let's say time t equal to 0 and t equal to pi. So you see, I mean, I think it's obvious. You see how this oscillates. And the mathematical description of this thing is, all you can think about the reflection of the incoming wave from obstacle, like a solid wave or something here, or just you can think about infinite string and two waves coming from opposite directions. And if you just take, let's say, cosine, two waves of this simple form, and you have linear equations, then you can construct new solutions just by adding these two terms. Then you get the formula as you may see here. And this is something that is like a characteristic pattern of one-dimensional standing wave. You have oscillations in space, cosine x, and oscillations in time multiplied by the oscillations in something that it's time. And of course, there is no need to restrict your attention to one dimension. You can go to two-dimensional standing waves, and the idea is very, very, very similar. So you can see standing waves like that. You have two snapshots at different instants of time as a superposition of this time four waves. So you have wave moving in opposite direction along the x-axis, and the wave moving in opposite directions along the y-axis. And the superposition is again periodic function times in time times the periodic function in space, as you may see here. And this kind of standing waves, I said that they appear in music, for example, but they appear in almost everywhere. So if you study quantum mechanics, then you may see electron in a box, seismic waves, violin strings, and many other examples. They could be also like optical waves of this time could be used in industry, acoustic waves as well to position small particles. So they have some practical applications. But in majority of the theories where they appear, they are just linear standing waves. So you have linear wave equation and you can add two solutions and construct a standing wave. But there is an interesting example. It's called Faraday waves, and it's known for many years. Those are waves which are essentially nonlinear. How they were observed and what is the link, because I'm going to talk about Einstein equations. So the link is by the equations that describe the system. Those are Navier-Stokes equations. But they were observed not in mathematics at the beginning, but just in experiment by Faraday. So imagine that you have like a piston or a plate with a thin layer of solid, of fluid. So it could be water, for example. So maybe the easiest thing is imagine that you have a plate and then you have a little water on this plate. And then you have like a oscillator, mechanical oscillator that gives vibration to this plate. I think you see me in the camera as well. I'm just showing this. And when the oscillations are small, so then nothing really happens. But when the amplitude of oscillations becomes large, then standing waves appear in this water. And the shape of these waves depends on the frequency, but depends also on the shape of the force. So if the force is given by some function, so it could be sinusoidal function, but it could be also like a sawtooth function or triangular function. So you can invent as many shapes as you wish. And this is interesting because as you know, there is some analogy between Navier-Stokes equations. There are nonlinear and Einstein equations. So maybe I don't know if this is correct or not, but maybe there is a hint that for Einstein equations you would have a similar complexity of this phenomenon of standing waves. To give you just example, this is not a simulation, but those are real photos. So imagine that you have a plate, water on this, and you have a camera above this thing. Then at different instance of time, you can take photos, pictures. Okay, and you have, if you take these pictures on different phase, you can overimpose them, so make a composite photo here. And there is something magical here because there is enormous complexity of the patterns that you can achieve. So in other words, the linear standing waves are boring because you just do superposition of waves moving in different directions. But nonlinear waves, as this Faraday waves examples show, it's much more interesting and complex. And those are just 3 examples, but you can have like, I don't know, tens or much more shapes that you can that can appear here. And there is, of course, mathematical question. This is observation. So this is real experiment and photos of that. But the question is how to calculate those things, how to predict which shapes are possible, why this shape is in particular, it could happen, why it depends on the shape depends on the frequency of the shape of this force, which gives perturbation to the system. And the people studied this for almost 200 years. I mean, so the experiment was done in 1831. This is more or less the time that Navier constructed with Stokes a little bit later his equations, their equations. And there is a lot of mathematical work done on this subject, and people try to understand it. Okay, so this is just a hint to I will try to convince you that the standing gravitational waves, they could be interesting. Here, this is a result of simulation, I think, because here we have a spherical symmetric system with polar symmetry, I would say. But here, sometimes you could have pattern like this. Yes. So the brighter spots are just like top of the waves in this situation. And of course, there is a question what kind of patterns could appear. And this, if something like that would happen in general relativity, this would be very interesting because you would have like a local concentration of gravitational energy in these bright spots in this situation. So they looks from outside like some kind of particles. Yes, for test particles, they look like small masses or something like that. Okay, but this is just like a fantasy. So we are coming back to Einstein equations and what can be done at the moment. So when you study literature from general relativity on standing waves, then you will see the standing gravitational waves in several places. The first thing is like Goldie standing waves. So in the original paper by Goldie, he already used this name. So this is a class of cosmological models, and one can think about them as a superposition of wave moving along the torus in different directions. And there are simply standing waves. You could have in numerical relativity like a standing wave boundary conditions. For some reason, sometimes it's easier to to give energy. I mean, not only lose energy, but the gravitational system like two black holes orbiting, but also give some energy to the system, so you could have like a more stable configuration. But this is like technical thing. If somebody believes in inflation, then you could study the premolar gravitational waves from inflation. There are simply tensor perturbations, and they are simply standing waves. But this is in linear approximation, as far as I know. And here you have reference for the Stephani paper. Okay, so the first question is, and this is question which was addressed by Hans Stephani, how to define the waves. So one way of doing that would be just say that this is a superposition of waves moving in opposite directions. But this is problematic because equations are nonlinear, so you cannot have a direct superposition. Sometimes you can do that at some deeper level. And another thing is that if you try like superpose waves, and we assume that the waves are coming from infinity, and the space was initially between them was flat, then there is like a rule that you will see some singularities. And the most famous and basic studies of this topic was Kahn and Penrose, and this was in early 70s, I think. Okay, so it's not trivial to superpose gravitational waves. Of course, you can do that in linear approximation, but this is again trivial and not so much interesting. You can try to do that in terms of the gravitational energy density, because what is the standing wave? You see, you have some kind of wave, and the energy is changing. I mean, there is an energy in these oscillations here, but there is no transfer of the energy. So you can try a different definition, like in terms of the flux of the gravitational energy. But in general relativity, you can construct the pointing analog of the pointing vector in several waves, but I think up to my knowledge is not clear. I mean, so the whole problem that you see here with the definition is that the gravitational waves are, and the energy that they contain, it's like a non-local phenomenon. So it's hard to give the local description. So one way in which we try to approach this problem is related to the Professor Trautmann paper from 1958. So he studied their boundary conditions in analogy to electrodynamics, which should be given for the space-time that contains gravitational radiation. And one of the results in this paper was that the Ricci tensor should have far away from the sources, should have a particular form. We know today this form as a null dust. So I think it's the first article where this null dust, up to my knowledge, where the null dust appeared. What is null dust? Null dust is like a effective description of the gravitational wave in terms of the energy momentum tensor. And so you can get it from the considerations near the infinity, like Professor Trautmann did, but you can obtain it in a different way in so-called high frequency limit. And so if you have quadruple formula, the famous quadruple formula for gravitational radiation, and you want to estimate energy that was radiated from the system, so usually this is done using so-called Isaacson approach, where you calculate energy momentum tensor of the gravitational radiation in the high frequency limit. And this was put on more mathematically firm footing by Barnett, and later in more general context by Green-Wald in 2011. So there is like a procedure. If you have a space-time, then you can take, and some kind of perturbations, maybe gravitational waves, you can take a high frequency limit and see what you get in the limit. And the null dust has a form of this part of this energy momentum tensor. So you have some density that is function of position and a null vector. So what we proposed with Adam Cieślik, like already 2 years ago, was that we try to define standing gravitational waves by the high frequency limit. So if this is good approximation in high frequency for the gravitational radiation moving in one of the directions, then if you take the wave vector, which is oriented in opposite direction in space, I mean the spatial part of this wave vector, and you make a superposition of that, then you will have like a high frequency limits of standing waves. And we provided examples of exact solutions that in this limit reduce to this form of the effective energy momentum tensor. So there is like an example that this works. Yes.
May I ask a question?
Yes, sure.
Hello, this is Lewandowski. So those solutions are algebraically special?
They are, I mean, the solutions that we use as example are not.
Oh, okay, okay. The reason I'm asking is that in the case of algebraically special solutions, then solving for null dust, actually, I mean that there is a general solution with null radiation. I'm not sure about null dust, because dust is, I understand, massive. Oh, I see. Okay, so okay. So what
this is null vector. This is null vector.
Oh, this null. So this is I null. Would call it null. Okay, null dust. Okay, so we just call it the radiation, I guess.
Oh, okay. So there is different terminology.
Okay. Okay. So my comment is that if you consider algebraically special solutions, then you assume that this degenerate direction of the Weyl tensor is at the same time coincides with this null direction of radiation, then those solutions are basically explicitly known. So
but you mean the known in the sense the whole family of solutions?
In the sense that you can explicitly solve all the Einstein equations.
Jurek, but here there are two of these null vectors.
Yeah, this is here I can see that
away from this what you are talking about.
Okay, so my comment is about some other class of spacetimes which are algebraically special and which have just a single null radiation. Okay, thank you.
Mm-hmm. And I was presenting this result in Vienna some times ago, and there was, so I do not know the counterexamples. So to have a spacetime that has this kind of a limit and it's not a standing wave, but it was pointed by Piotr Hruściel and Eichelburg to me that maybe it's not the best way to define some class of solutions in terms of the limit, for the simple reason that in the limit you lose some information. So there could be like solution with different properties, but they could have this kind of limit. I don't.
May I ask
Yeah.
a question?
Yes, sure.
Do you want that this condition for energy momentum tensor or Ricci tensor is far away only or everywhere?
This is everywhere.
Okay.
So in the paper by Trautmann, this was near infinity, yes, but here it's just everywhere. Okay, so we propose this definition, and we know in several examples it works, but maybe it's not clear that maybe they exist counterexamples, some strange solution. I mean, the existence of this high frequency limit, there was like a hot debate in a completely different context, in the context of the effect of inhomogeneities in cosmology, because of the Green and Wald paper, but it's a different story. And there are some general results on if you have this kind of high frequency limit, if there exist solutions that for which this is the limit. Okay, so this was the question. It was not clear, but this is not the general result. It's like in some special cases. Okay, so but as I saw you here some nice images. Of course, this is like a fantasy, what maybe could be achieved, but we want to start with something simple. So we want to start with the example of a standing wave, just one-dimensional standing wave. And we follow the procedure that was suggested by Hans Stephani. So since we don't know what the really standing waves are and how to define them, then just look at something, at exact solutions that look like a standing waves. And by look like standing waves, I mean the metric functions are of this type. And then try to study them to convince, to find arguments that there are really standing waves, or maybe there are not standing waves, using some different methods. But what you need, I mean, in the simplest model, then you need something that depends on, if you are in 4 dimensions, something that depends on 2 variables. One of them should be time. So you want to get rid of 2 variables for simplification. So you take this G2E group. Then you are interested in the abelian group to have a metric in a simple form that is not dependent on this coordinates. I mean, that the metric could be adapted to the symmetric coordinates, I would say it that way. And in some special case, again, you can write it in this form. And if you are interested in space-like orbits, as we are, then you are this line element of the most general form of this form, where P, omega, and F are functions of T and Z. And for those solutions, I mean, this type of solutions were metrics were studied, and we know that there is like an equivalence. So once you find a solution here, by a complex substitution, you can go between cosmological spacetime like Gaudi solutions, cylindrical spacetimes like Einstein-Rosler waves, or stationary axially symmetric spacetime. So we are this time not interested in this thing, but sometimes it's useful to jump from cosmological interpretation to the cylindrical spacetimes to find a model. And of course, those are the same formulas, but they have a different physical interpretation, and like geodesic equations and other phenomena are different, and different things could happen.
In the previous transparency, you said G2. So when you say G2, do you mean what mathematicians call G2, or you just mean 2-dimensional group?
I mean what is in this big book on exact solutions, so that there are 2 killing fields.
Ah, okay. So you mean something else. There is some other class of
Okay.
G2 groups which may be confused with this. Okay.
Okay.
Thank you.
Okay. And now, I mean, this solution that we have here, and that could be used, in our opinion, as toy model of standing gravitational waves, they are quite complicated. So for simplicity, I will not show you in one slide the full form, but I will substitute the function, some functions there, and I will give these functions later. And what you have to know about those functions is that they are like periodic in a special variable, like in Z, and almost periodic, quasi-periodic in T, almost periodic in T. And they are of this form. So one thing is the most standard thing, and this is what we studied with Syed Naqvi. So it's like a T3 Gaudi, and this is a particular solution in this class, and that has a simple form. Then you have unpolarized Gaudi, and I think that this is something unusual because usually, I mean, it's well known that here you can have all the solutions in exact form, but here usually are numerical studies, and we found this solution using this equivalence. So we took Hali-Sol spacetime. So this is a cylindrical spacetime with cross-polarized gravitational waves, like a generalization of Einstein-Rosen, and we wrote it in a cosmological form. And we got this kind of a solution. So here you have one more additional parameter, alpha. And for alpha, particular value of alpha, alpha equal to 0, you get, you recover the simpler polarized Gaudi solutions. Okay, and we had a preprint on this. It has not been published yet. And there is the third thing that it's different from these two things is non-vacuum electrovac spacetime electromagnetic Gaudi. So you are not in vacuum, but you have some field, additional field here, and this is the work in progress at the moment. And here you see this periodic and almost periodic functions, S1, R1, Q1, Q1. Those are the same functions, Q here and Q here for different solutions, because there is like a common pattern that appear, and I give you this function here. So they are given in terms of the Bessel functions of the first kind and some constants. Okay, so you have the spacetimes. They look like a gravitational standing waves. And what can you do for them? So one method that to find out what really happens and how these waves looks like in the spacetime that we've found is to study geodesic deviation equation in the orthonormal frame of a freely falling observer in the spacetime. So, and this is particularly convenient if there are stationary observers, and this is the reason why we study this cosmological version of solutions, not cylindrical spacetime. Why? Because it turns out that when you have standing waves on a torus, that there are stationary observers in antinodes. So you can set the orthonormal frame there and study geodesic deviation at antinode. If you would move to the cylindrical version of the solutions, then there are no stationary observers. So if you set observer with initial velocity relative to the coordinate system 0, then the observer is attracted by the central part of the standing wave. And the reason is simply as follows, because the amplitude of the standing waves in the cylindrical case falls down with the 1 over rho, where rho is the radial coordinate in such spacetime. So you have like a huge amount of the gravitational energy at the center and less outside. So the test particles is something like a effective rod attracting things gravitationally. So there are no stationary solutions, but here we have stationary solutions. So we can see what happened with test particles near such observers. And of course, using Newman-Penrose tetrad is a useful thing. We try optical scalars as well as laser ranging, and the Bell-Robinson tensor. And of course, the super energy density is not energy density of gravitational waves. but somehow we can calculate it, and it satisfies our expectations, how the profile look like, and such things. Okay, so Newman-Penrose tetrad. Just one more question. I have 45 minutes or 1 hour?
You have 1 hour, let's say.
1 hour. So I still have some time, yes? Okay, because we started 1/4 past. So this is a well-known thing, Newman-Penrose tetrad. We introduce this Newman-Penrose tetrad in terms of the orthonormal tetrad, like the standard thing. And then we look at the geodesic deviation equation. And here, the components in this frame, the components of the Riemann tensor plays role of the gradient of the force. But I like to, I think about this now in the following way, that is like a Newtonian equation, and you have like a spring, and this is this coefficient in the spring. Okay, when you have, this is deviation vector, so this is the vector that gives you deviation of the position of the particle from the freely falling observer. So it's large, then it's far away. And here you have like in Newtonian analysis, the constant of the spring. And of course, these quantities are calculated at the position of the observer. And again, this is not the new thing. It's from 1965, I think, by the paper by Sekeres called Gravitational Compass, where the interpretation of the components of the Weil tensor in this null tetrad were given by exactly by the geodesic deviation equation and the effect they have on the geodesic deviation. So here I present this for this model with electromagnetic Gaudi, because it has most interesting form. So here you see the components. This is written in the orthonormal frame, and here you see the components of the Ricci tensor, and they should be components of the Weil tensor in the orthonormal frame, but they are converted to the components of the Weil tensor in the Newman-Penrose tetrad. So okay, but this is general formula. So you have R stands for the real part, because those coefficients are complex, because the frame is complex. But we have to evaluate this at the position of the observer, and the stationary observers are at antinodes. So when we evaluate this at the position of the observer, it turns out that almost everything cancels. So these terms that comes from the solutions being non-vacuum, they are non-zero, but they cancel one each other. In this situation, R2, 3 vanishes. So you get, in fact, something that we get for all these models, this kind of formula for those coefficients. So this is, you may think about this as a spring constant along z-axis, and this is the longitudinal direction. So this is direction, you don't have a propagation of the wave, but there is like a, it's like a x-axis here, yes? So this is, and you have two orthonormal directions. So this usually is associated with the deformation that are done by the gravitational waves. So those are the spring constants in these directions are 2, 0, 2, 0 and 3, 0, 3, 0. So it's like x and y, and this is z direction. So the first thing you see here was that if you have a space-time with psi 4, let's say, then it's like a pure radiation and other remaining terms equal to 0. So it's like a pure radiation. If you have with psi 0, non-zero, and psi 4 equal to 0 and remaining equal to 0, it's like the radiation, pure gravitational radiation, moving in the opposite direction. And here we have something like a superposition of radiations of moving in opposite directions. So we have non-zero psi0, non-zero psi4, and they are equal. And moreover, there is psi2, and there is a theorem by Szybka that says that you cannot have solutions with psi0 and psi4 non-zero and remaining all the terms equal to 0. And this is usually interpreted in this way, that when you have a superposition, like nonlinear superposition of waves moving in opposite direction, then it's always some kind of an interaction. And this psi2 is called like a Coulomb term, because it gives you some particular effect on the test particles in this frame.
But this second result is in the Ricci-flat case, and you are not considering Ricci-flat case, right?
Szybka is in the Ricci-flat. Then I'm not sure. But okay, so this is, I was showing these formulas for the electro-vac spacetime, but they are the same. The situation with psi0 equal psi4 is the same in the remaining two models that are vacuum. So I don't remember if Szybka's theorem cannot be applied to electro vacuum, but as a result of calculation, I mean, this psi2 is non-zero also in this case. Okay, but this is thank you. This is important remark that can be checked. Okay, if this cannot be avoided in electrovac spacetime. But of course, in vacuum, in pure vacuum, it is two remaining models in vacuum. This holds as expected. And there is a question how to present the effect of the waves in some convenient way. And I apply something that you know very well, because it appears in this all in the old book on gravitational waves. But not all people know that those things could be called a Tissot diagram, and they were introduced in cartography. When you have a projection of the surface of the Earth on the flat surface, then you have always some kind of a distortions. And when you look at the map, as we do, it's not clear how these distortions looks like. So if you have distances, how they change, and there's this idea by Auguste Tissot that you can make like a plot on the map. What is the deformation of a circular region on the surface on the Earth? And you can apply this idea to see what is the effect of gravitational radiation. And I think Gary Gibbons was the first who introduced that to relativity. And so you can see this kind of diagrams. I mean, in every book for gravitational, linearized gravitational waves, and in other cases, like for plane waves, in this paper by Gibbons and Horvath and Duval-Zhang, and in our paper as well. So this first, I will show you the standard image, standard picture. So the standard picture for linearized wave is that you have some test particles that you may study, put their positions. The wave is coming, and the coordinate positions of the particles did not change. But if you take slices with the proper with time constant hypersurfaces, and calculate the proper distance along those hypersurfaces, it turns out that the positions and distances between these particles are deformed and change. And you may see it here in this case of standard polarization, and for cross polarization like here. And here, of course, in the linear approximation, if you can have like a periodic source, like let's say neutron stars, we have not observed this yet with a bump, neutron stars with a bump, We have not observed it yet, but it's I think it's possible and in some sense expected to see such things. Then this pattern will repeat at infinity many times. But if you have a wave with like a compact support moving, when the wave is gone, so it goes through this position, it deforms the position of the test particles, but then flies away, then the particles return to its original position. Okay, but this is in the linear approximation. And what happens in this our model? This time I take the simplest model because I have the figures ready for this model. So the situation is a little bit different. Why? Because the Gaudi model is like a cosmological model that starts with the Big Bang and then expands anisotropically. And if you have a standing waves in this model, it's somehow obvious that the amplitude of the waves will decrease in time. So we have like a strong waves at the initial moment, and then amplitude goes down. So this is one thing. The second thing is that here we have nonlinear waves, and in this linear case, we have only transverse effect on test particles. But when we study the full nonlinear problem, we have a longitudinal effects. So here, the solid line represents the value of the component of the Riemann tensor responsible for the, let's say, Newtonian forces acting on these test particles along the z-axis, z-axis, and this is the axis in which the waves are not propagating, but this is the something what you will call the direction of the propagation of waves. And you see that it's order of magnitude smaller than the components of the Riemann tensor in orthogonal, in transverse directions. And in the transverse directions, again, as expected, they act in opposite way. I mean, if you have a contraction along the x-axis, then there is a stretching along y-axis. And if you have contraction along the y-axis, you have a stretching along the x-axis, and so on. What is interesting, that if you look closely at this longitudinal effect, so the components of the R1, 0, 1, 0 Riemann tensor, then it's not, it looks here like a symmetric attraction. I mean, if you have positive value, then this means attraction for the particle to the observer, and negative value means repulsion. But if you look more closely, it's not symmetric. And over time, if you look at longer times, the attraction dominates. In other words, it means that if you have test particle and you slightly perturb, you would be this observer, you would perturb this position of the particle in the direction of the z-axis, then it would move there and back, and finally it should be attracted to the antinode. So in this sense, the antinode are distinguished here. Okay, and how the Tissot diagram looks like. So instead of making slices, I draw with Syed, this is from our paper, this kind of tube. So what you can see here. So imagine that we set, we are in the center here, and we set a ring of test particles around us. And those particles are not moving relative to us at some initial instant of time. And now when you study this thing like a memory effect in other space-time, when you have the waves with compact support, then this is not problematic, this initial moment of time. Why? Because there is no wave, so there is no interaction here and no deformation. Then the wave is coming and waves go away, and you see what happened to this thing. Okay, so in the linear theory, the ring will return to the original position, but if you take into account for waves with a compact support nonlinear effects, then will be like a memory effect that will give some velocities to these particles, even if the wave won't be, will already be far away from this test system. But here we don't have this initial empty space-time. We always have waves. So the shape and evolution of these test particles depends in which moment we say that we release those particles. And to show that, I draw two tubes in the same diagram. So you can think, you see the first solid ring is squashed along the x-axis. This is Xi2, so it's like x-axis. So I know from this that if I look at this diagram, this dashed dark line represents the Riemann tensor, so the spring coefficient along the x-axis. So it had to be positive at the initial moment because this. So we started like somewhere, let's say here or here. Yes. And the second ring, represented by dashed line, was started released at a different phase, like let's say somewhere here. So it was squashed along different axes. And of course, the first wave had the biggest amplitude. So the effect was the stronger than the particles were moving, but you see the effect of the subsequent waves in this deformations here. But after some time, the amplitude of the standing waves, because the Gaudi expands, the amplitude of the standing waves is smaller. So you can say that the effect is smaller, but there is like a memory effect of the first initial interaction with the wave. Of course, and this cannot be defined clearly as usually people do, because you have the situation the waves are always there, yes? But it's like something similar to the memory effect, I would say. Okay. So I'm slowly coming to the end. If I still have time, I can show you, I showed this in Łódź already. But this is super energy density, so you don't think about this as a true energy, but like some indicators of what happened in the system. And I said that it could be useful because you see the solid vertical lines are antinodes, and those dashed lines are nodes. So you see that this energy density has an extrema and antinodes, and these extrema are not moving from here, but for different snapshots, and here you have one more parameter, but it's not essential. So let's look at the maybe the same value of parameters. So it's like beta equal 1. So it's the red thing. So the extrema stays there, but the another extrema that is not far from the node, it's moving to one side to the other side. And if you calculate the superpointing vector, it's like an energy transfer through some hypersurfaces. You see that there is no energy transfer through antinodes, and at the given instant of time, there is energy transfer through nodes in this coordinate frame. But on average, if we would average that, then this transfer goes to 0. So this is with expectations of what Stephani said. But of course, those are super energy and super pointing vectors, so we don't know if they represent any physical quantity. Let's say that there are some invariants that could be defined for relative to this system. And you see that exactly this super pointing, that there is exactly no transfer for all the profiles that we tested here through nodes. Okay, so let me summarize my talk. So, I mean, so there is still many things that we don't know about the standing waves, but we can somehow approach the problem with exact toy models. So although we cannot give the very precise definition of standing waves, they look like a standing waves and act on test particles as it's expected from standing gravitational waves. So we see this effect that antinodes attracts freely falling particles by the Coulomb component. So it's like a result of nonlinear superposition, I would say, nonlinearities of Einstein equations. But this we see only in this cosmological versions of the model. If you take, if one would study the cylindrical models, then you would not have a stationary observer at antinodes, and it's not clear how to distinguish a freely falling frame and how to do that to be able to calculate something. So this is like maybe particular property of a class of the models. And the Weiss scalars, this is as expected, the psi 0 is equal to psi 4. And so this looked like a convenient setting to study nonlinear waves, nonlinear gravitational standing waves. There is one more thing that when you study the nonlinear effects for the wave that is passing through you, then again, it's not so easy to do with the freely falling frame because there are these longitudinal effects that simply moves observer along the direction of the wave. And here, those effects cancel at the antinodes. So it's like a convenient setting to study nonlinear gravitational waves in general. Okay, so I lost my voice. But thank you for your attention. And if you have some questions, then I'm ready to answer.
Thank you very much for your very interesting talk. And now we have time for questions, please. Okay. Any comments or remarks?
May I ask a question?
Sure, sure.
Paweł Nurowski, so did I understood correctly that you defined the gravitational standing wave as space-time in which Ricci tensor is sum of two k-mu things where k's are null vectors in opposite directions, right? That's the definition?
No. That the space-time in the high frequency limit corresponds
what does it mean, high frequency limit?
High frequency limit, if you look at this solution here, you see they depends on the parameter lambda. So this means that if you have a Gaudi model and this is like a torus, so you have, let's say, 100 waves, standing waves on that. But if you change this lambda, then you have 1 million waves. And then you go with the solution to the limit. So it's like in the limit, you have infinite number of waves, but the amplitude, I mean, there are this high frequency limit are defined in this way that they take into account that the amplitude of the wave could go to 0, but there is like a non-zero derivative of the perturbation to the metric. So,
okay, so I still don't understand. So you are you telling me that you defined what a gravitational standing wave is only for this kind of class of metrics, like this matrix with abelian two-dimensional symmetry, only for those, or for some other, or for general ones?
Okay, so this was a proposition to define it in general setting, but it was tested only with one example in this particular setting, and there are some doubts if you can do that in this way.
No, but this lambdas, this t that you have, this refer to some coordinates somewhere. So somehow.
Okay, but the high frequency limit, one would have to look at the paper by. I mean, the most mathematically advanced version is this Greenwald, paper, and is defined in general case. So it's not only
Okay.
defined in cosmology, but in general case. So
Okay.
you have a space-time, you have some kind of perturbation, and then you can take the high frequency limit and see what kind of effective energy momentum tensor you get in the limit.
Okay, so you define. Let me repeat what you have just said. I want to understand. So you define what is standing wave only in this high frequency limit case, whatever it means, right?
Yes. So this is what we propose in the physical review paper.
Okay, thank you.
But as pointed by Piotr Schuster and Ascherburg, there are some doubts if you can use the definition because you lose information when you take the limit. Okay, so what I'm doing now, so it's not I'm just using I have a standing wave only this limit works. I try to look in the way that was suggested by Stephani. So look at solutions that look like a standing wave, study them, and then try to see what kind of properties they have. So this is, so I mean, so this is like a proposition of the definition, and not fully. I'm not fully sure it's valid, but I don't know the counter examples, so I don't know it's not valid as well.
Okay, further questions, please. Comments, remarks? I can't hear any, so let me have my question. Have we already detected standing gravitational waves? I mean this LIGO Virgo observations.
I mean, not we have not detected, and it's so the first question is where you can see them in the when you can expect them in astrophysical setting.
Yeah.
And of course, if you are two waves going with opposite direction and they collide, then what you can expect that. But this is very unlikely that we will be exactly at such spot. You can expect that in a cosmological setting. I mean, the people do that such things that they try to predict this primordial gravitational waves and their statistical properties from inflation. But they for sure, I guess that the nonlinear effects are probably not important there. So those kind of waves were not detected, and I don't know the obvious setting in which they could be expected. Maybe in cosmology, but not nonlinear effects. So this is like a theoretical study.
Okay, thank you. Nikolai, please.
Yes, so my question and comment is a bit related to the previous one. So there is an experiment going on using something called pulsar timing arrays, where people look at a number of pulsars in order to detect the background gravitational radiation. It's more radiation created by supermassive black holes throughout the whole universe. And what people assume there is that this background has the form of something somewhat similar to the standing wave, namely some kind of Gaussian random process. So this feels like the closest astrophysical analog of standing waves to me. So broad frequency band and waves propagating in all directions, creating some kind of random Gaussian field.
Okay,
but
so
certainly treated in linear way.
Mm-hmm. Okay, so that's interesting in this context.
Okay, any other question? I can't hear any. So let us thank the speaker again. And we close the meeting.